This is lesson 2 in our unit on writing chemical names and formulas. Today we want to learn how to name and write formulas for binary ionic compounds containing transition metals. Before we begin our new lesson, I'd like to review the previous lesson. So if you could please find Learning Check 1 in your notes, we will go over the answers to those questions. The first 3 questions ask you to complete the names of 3 simple binary ionic compounds. You know they are binary because there's only 2 elements in the compound, and you know they're ionic because there is a metal bonded to a nonmetal. In the first example, sodium and iodine are bonded together. You change the name of the iodine to iodide, but otherwise the name stays sodium, and then it becomes sodium iodide. Next, we have potassium. Potassium and bromine joined together make potassium bromide. And then magnesium is joined to sulfur. The name of that compound would be magnesium sulfide. In the previous 3 questions, there were only 2 ions. Now we have 3 more questions in which there are multiple ions. We see subscripts are involved. However, in ionic names, you do not give the number of ions involved in the formula. You just name the metal and then the nonmetal. So in the first question on this slide, we have calcium chloride. Next, zinc iodide. And next, aluminum oxide. In all 3 cases, the ending of the anion, the negative ion, changes to IDE. The metal ion is simply the metal name. In this set of questions, you are asked to put together the formula. The rule is that you use a ratio of ions such that the compound's overall charge is 0. In other words, ionic compounds should be neutral. So in the first question, sodium has a +1 charge, sulfur has a -2. You need 2 sodiums for every 1 sulfur, so the answer should be B, Na2S. Next, aluminum +3, chloride -1. You'll need 3 chlorides for every aluminum. So aluminum chloride's formula is AlCl3. And then in number 3, we have magnesium +2, nitride -3. We can use the crisscross method, and the formula would be C, magnesium nitride, Mg3N2. In the first lesson of this unit, we learned how to name binary ionic compounds involving the alkali metals and alkaline earth metals, groups 1 and 2 on the periodic table, and a few other ions such as aluminum, zinc, cadmium, and silver, who have ions that always have the same charge. But we've left out a big group of elements in the center of the periodic table known as the transition metals. They are known as transition metals because they can have more than 1 ionic charge. Because transition metals can have more than 1 charge, you can make more than 1 formula with them. Therefore, we need a way of writing a name for each charged atom in a unique way. The whole point of making chemical names is to make sure that the name uniquely identifies the formula that goes along with it. So in the case of the transition metals, what we do is add Roman numerals to the metal's name in order to tell what the charge is. Just in case you don't remember your Roman numerals, we only need numbers 1 through 4. So in our European version of the Arabic numbers 1, 2, 3, 4, the corresponding Roman numerals are represented with an I, II, III, and IV. So, here are some examples of ions of transition metals. First, Fe2+. We have to give the charge in Roman numerals, and what we do is add parentheses to the end of the name iron. So the first example would be iron, II, or iron 2 ion. Next, the iron 3 ion is iron, parentheses, III, close parentheses. You notice there is no space between the name and the parentheses. That Roman numeral becomes part of the name. And finally, my favorite ion, tin-4. TIN, parentheses, IV, close parentheses, the tin-4 ion. If you'll look in your textbook on page 255, you can see a list of some of the more common of the transition ion charges. Just as our last lesson where we were naming simple binary ionic compounds involving things like the alkali and alkaline earth metals, you keep the name of the metal the same. The thing is that when a transition metal ion is involved, its name also indicates its charge in Roman numerals in parentheses attached to the name. There is no space between the name and the parentheses. It becomes part of the name. So the rule is actually the same. Name the metal ion the same as the metal, and then name the anion IDE. So FeO would be iron 2 oxide. IRON, parentheses, II, close parentheses, iron 2 oxide. Next, we have manganese phosphide. But it's got to indicate the charge because manganese can potentially have more than one charge. So properly spoken, it would say manganese 3. One of the things that you need to be able to do is see a formula and give a name. In the case of a transition metal, that name has to involve its charge. So, what if we had the formula FeO, for example? Which iron ion is that? What you do is take a look at the anion, figure out its charge, and then see what it would take to neutralize the compound. For example, in FeO, O has a -2 charge. We know that by looking on the periodic table, noticing that oxygen is in column 16. They have 6 valence electrons and will usually, well, almost always, gain 2 more electrons, become a -2 anion. So in this case, if oxygen is -2, the Fe must be +2. So the name of this compound would be iron 2 oxide. In MnP, we saw that we called it manganese 3. How did we know it was +3? It's because phosphide is in column 15. Those anions take on a -3 charge. They gain 3 electrons. If there's a 1-to-1 ratio and phosphide is -3, then manganese must be +3. Manganese 3 phosphide. One objective for this unit is for you to be able to see the formula and give a name. The other objective is for you to see a name and give a formula. They should uniquely correspond to each other. So what if someone said, what is the formula for copper chloride? The proper response would be, which one? Copper is a transition metal. Like most transition metals, it has more than one ionic form. In this case, you have two choices. Copper sometimes appears as +1, sometimes as +2. For example, if you have copper 1 chloride, then the formula would be CuCl. The copper is +1, the chloride is -1. You need a 1-to-1 ratio. On the other hand, if you had copper 2 chloride, copper with a +2 charge, then you need a 2-to-1 ratio. And so the formula would be CuCl2. Let's practice a little bit. If you had the formula FeCl3, the iron ion must have a +3 charge because the chloride is -1 and you have 3 -1s. You only have a single iron, so it must take on all the positive charge. It must be +3 to neutralize this compound. The name of that compound would be iron 3 chloride. The Roman numerals give the charge. CuCl, we just saw in the previous slide, the copper would be +1 because chloride is a -1. There's only one copper, it must be +1. Copper 1 chloride. If tin has a +4 charge, we call it tin-4. So tin-4 joined to fluorine would be tin-4 fluoride, must have a formula of SnF4. Fluorine always has a -1 charge. The tin has a +4 charge. The only way to neutralize that compound is to have 4 fluorines for every 1 tin-4 ion. PbCl2, the lead has a +2 charge, so its name would properly be lead-2 chloride. And finally, we have Fe2S3. The iron in this case must be a +3, iron 3 sulfide. You can figure out the charge when it's Fe2S3 by doing the reverse of the crisscross method. If the Fe is 2 and the S is 3, then the Fe must be +3, whereas the sulfur must be -2. Now, just to introduce a little confusion into the process, the point of a chemical name is to be able to find the unique chemical formula that goes along with it. On the other hand, chemical formulas actually can have more than one name. That's because there are competing systems depending on the branch of chemistry that you happen to be dealing with, the age of the compound, when it was first discovered or named, and so forth. Just as an example, sometimes you find a Latinized version of some of the transition metal names, such as ferric or ferrous. The name iron 3 is called our stock system name. The stock system was invented in the early 1900s by a chemist by the name of Alfred Stock. The old name for iron 3, though, was ferric. The old name for iron 2 was ferrous. Now, I don't want you to memorize these names. I just want you to recognize that if you run into names like ferric, ferrous, cuprous, cupric, then you need to go and look that name up. It has something to do with giving the charge of the ion. The IC version of the name is the higher charge. The OUS is the lower charge. Here's an example from a toothpaste product. You can see the chemical name stannous fluoride. The stannous refers to tin, and specifically that would be the tin-2 ion. Also, I want you to make a note of a special situation that occurs with mercury. Mercury can have two charges, +1 and +2. Now the +2 ion acts just like every other ion, and you would write it as mercury with the Roman numeral 2 after the name. The mercury 1 ion, on the other hand, is rather unique in that it is a diatomic ion. Two ions of +1 charge each are always bound together. So whenever you find mercury 1, it will always be written as Hg2. Here are some examples. Again, Hg with a +2 charge is called mercury 2, written with the Roman numeral 2 after the name mercury. Formulas include things like HgCl2. The Cl chloride has a -1 charge, so you need two of them to neutralize the +2 charge. You only need one oxide, which is a -2, to neutralize the mercury 2. Mercury 1, on the other hand, is always written as Hg2. It pairs up with itself, so it has an overall +2 charge, but you keep the name of the charge whenever you're naming the compound. So Hg2Cl2 is mercury 1 chloride. That's rather strange. We normally don't have two 2's in an ionic formula like that, but in this particular case, you have to do that because that's the way you find mercury 1 in nature. Mercury 1 always exists as a diatomic ion. It's the only one of its kind. And now it's time for some practice. If you haven't already done so, please complete Learning Check 2 in your notes. And then you should be given or pick up Worksheet 9-2, Naming and Writing Formulas for Transition Metal Compounds. Complete it to the best of your ability by yourself so that you can practice learning how to do this, and then turn it in to the inbox on Dr. Kemp's desk.